Okay, thank you for the introduction, Odile. Yes, so it was quite a challenge for me to do this presentation. It's the first time I do kind of an integrated presentation on the problem of environmental effects. Although it was all in my head, I needed to put it in kind of a logical order for presentation. And as you know, I'm quite eager at doing nice presentations. So I spent quite a lot of time on this one. I hope you will enjoy it. Um, and I've been working on the topic for actually more than 15 years. This mitigation of environmental effects. I started with vibration-based measurements, and now I'm doing it, as you said, with ultrasonics. But so I'll try to give an overview of the first part is going to be more theoretical. Of course, I will show some examples. It's not going to be all theory. And then I have a second part which is really related to applications from my research. So the context, of course, you know that SHM is necessary because we have problems like the collapse of this bridge in 2018. We have similar problems with aircraft of different types of infrastructure. But of course, the problem when you put an SHM system is the robustness of this one. And that's probably the reason why they are not commercially developed on structures at this stage, because you have problems like sensor error or failure, hardware problems in the acquisition systems, can also be software problems, and you have problems related to environmental and or operational factors. I'm saying and or because for me, environmental and operational is really the same kind of issues, and you deal with it with the same type of methods. But I will of course focus here on environmental factors, and all of these problems can cause false alarms. So the system can trigger an alarm because something happens, something else than damage happens. So that's really what we want to avoid. So if you have a bridge, for example, it can be exposed to day and night variations, to rain or wet conditions, to some very cold situations with, for example, a load due to the snow accumulating on the bridge. And you can have different number of cars passing, so changing the load. So the last two here at the bottom are more what we call operational conditions, because it's really the weight of the cars that change. These are more environmental, but as I said, you can deal with them with the same type of methods. Now, the question is strategy. So how are you going to tackle this problem of the fact that your measurements are going to change due to environmental factors such as temperature, humidity, etc.? So first, I have a question here, and I don't know if it's possible in Zoom to put a thumb up and down, but I would like you to vote and say if you think that we need to understand the effects of temperature and humidity on factor to compensate for them. If you think that's the case, put a thumb up. If you don't, if you think it's not the case, if it's possible, put a thumb down or don't answer anything. Okay. Okay. So what's your opinion? Okay. So I see Jasmine is saying you need to. Yeah, I'm sorry, I don't have all the first names, but I have four saying yes, you have to, 4 or 5. Yeah, and then some change their mind. Okay, so it's a good question. Like, should you really understand what's going on if you want to compensate? So I think both answers are correct. Because from my point of view, if you say, yes, I need to understand the effects to compensate for them, then the way you will compensate for them will depend on the type of measurements, because the effect is different on each type of measurement. It will also depend on the structure and the system. If you say no, then it means that it might be possible to find a solution that works for all, because it doesn't depend on what you understand or don't understand about the structure. So I'm going to use what I just invented a few days ago when I was preparing this. It's called the Swiss knife theory. So the Swiss knife, if you've used one, can do a lot of things, but it's not the most efficient tool for a specific problem. So for example, if you want to open a bottle of wine, this is going to work, but it's difficult because you have to put a lot of force on these kinds of Swiss knives to get the cork out. So you might want to use a cork driver, which works better for this purpose, but it cannot be used to do much other things, okay? So the Swiss knife is going to be a general tool, while the cork driver is going to be a specific tool. And on top of that, of course, the question is, are we using the tool properly? Because if you're going to take a cork driver and you want to cut cheese, well, I think you're going to make a job, but quite a dirty job of cutting the cheese. You might as well use the Swiss knife. So it means that you need to have a good understanding of the physics of what's going on if you want to use the specific tool like the cork driver. If you're using a tool that is specific but not, you don't understand correctly the physics, it's just not going to work. And so for a generic tool, it is less of a problem because you don't really need to understand so much of the physics, okay? Now, if we go to SHM, what is the major problem in SHM? And I think that's something that Chuck Farrar told me. If you're in SHM, probably you know who Chuck Farrar is. He works at the Los Alamos laboratories and did these very interesting state-of-the-art reviews and a lot of work on SHM. And he said, you know, the main problem we have in SHM is that we don't have damage sensors. And so the fact that we don't have damage sensor means that we need to evaluate damage from other measurements. And these measurements can be vibration features, ultrasonic feature, even electric measurements, etc., etc. And then the problem is that all these features, they are also sensitive to environmental trends. So we need to remove these trends to get to damage. So it's not a direct measurement of damage, it's an inverse one with some confounding factors. So it's a difficult thing. Now I'm going to take an analogy, which is the fact that if you think about comfort of people in houses, for example, we don't have comfort sensors. So there is no way, unless you ask some people, okay, to measure if they feel comfortable in the house. So it doesn't exist. So how do you do it? Usually, you will evaluate the comfort in the house from other measurements, such as the most common one is temperature. Okay, and this is why you have these thermostats in houses, because you measure temperature and from the temperature know if it's comfortable or not. But the point is that it's not because it's 20 degrees that it is comfortable in the house, because maybe there is humidity, maybe there is temperature gradients, you know, the heat is flowing from left to right, etc. Or maybe you are just a different person. Each person is different. Maybe you like 19 degrees, I like 22, etc. Okay, so it's not that simple. Okay, so the first thing I want to talk about here is, does temperature, for example, explain it all? So if I take ultrasonic measurements, I will come back to that in the second part, but we are doing ultrasonic measurements with embedded transducers in tunnels, okay? And so we are sending waves here in the roofs of tunnels. And this is the type of measured waves that we see. Just believe me now, I will show more in the second part. But from that, we can compute such what we call a correlation coefficient. So it means we take the first wave we measure at some point, and then we see how it evolves with time. And if the wave doesn't change, this is 1. If it changes, it's going to decrease. So this is, for example, a 1-week test in a Rogier tunnel from July 14 to 23, where you see the evolution of the correlation coefficient. So it starts from 1 at the first day, because this is our reference. So you see that it can change quite a lot, and you have daily variation. So this is what happens here. But you also have what I call seasonal variation, because you see that it's not the same every day. So there is a trend from day to day as well. Now, what is even more interesting is that if you plot this correlation coefficient not versus time, but versus temperature, this is what you get. And each color represents 1 day. So what happens if you look, for example, here at the blue one, I don't remember which day it is, probably in the last days here, because it's around 0.4. But you see that it makes a loop. And you see that for the same temperature, you can have 2 different correlation coefficients. Okay, so somehow there is another factor affecting here than temperature, or there is some delay or hysteresis, because it's not a one-to-one relationship. And so what does it mean? It means that maybe the temperature probe is not located at the right place because this happens in concrete and we are measuring in the tunnel. But maybe there are also other factors that affect the waves, like humidity, changing load, etc. Or there is just material hysteresis, the fact that the properties don't change directly with the temperature. There is some time delay between them or time-dependent low between them. So you see, this is really complicated because it means that it's not only by measuring temperature that you're going to have a way to get rid of the changes, because there are different measurements for the same temperature. Okay. Now, coming back to my analogy of temperature regulation in a house, you know that usually you measure temperature, and then from that you're going to use a heater, and you're going to have some kind of control load telling you, okay, it's too cold, so now please put some heating so I feel better. So there is a feedback loop. But the question is, where should we measure? Because is the temperature uniform in the house? So if you just put one thermostat in the living room, and then you have rooms in other floors, are you going to achieve a good temperature as well if you have only one thermostat? Is the heating capability the same? Because you make a control low, you're saying I have to heat that much, but maybe your heaters are bigger in a room than in another one, and so you don't reach this comfort everywhere. Okay, so the question is, maybe you should use multiple thermostat, not put temperature only in one place, but at different places. Okay, and then you can come to another question, which of course is unrealistic, but just to explain you, what happens if the house is filled with water now? So is this regulation law that we said to heat the house still good? Probably not. You know that, of course, water takes much more time to heat than air does. Okay, so if you use this regulation law, you are never going to get to the right water temperature. Okay, so that's what I want to stress, is that there might be a lot of delay between the command that you give and the fact that it's hot or warm and comfortable in the house. Okay. So that was just to introduce some of the problems we face when we want to deal with environmental effects. And I introduced the Swiss knife and cork driver theory. So I'm going to give you a few examples here, simple example and theory about that. So the cork driver example, remember the cork driver is when I want to use a really specific tool, which requires me to understand the physics. So this is a test that Jitendra did of two concrete blocks that are put in a climatic chamber. And in this climatic chamber, we have two, I say between quote, identical concrete blocks, because they are made from the same concrete, the same mix, the same procedure, but they were not made on the same day. They were done from a different batch, but they should be close to identical because it's the same components and the same mixing, etc. In the chamber, temperature and humidity are controlled, and we keep constant humidity of 60%. And then we varied the temperature, and we measured through the ultrasonic waves, we measured the change of wave velocity in the medium, in the concrete blocks. Okay. So first thing we notice is this is inside climatic chamber. This is what we assign to the climatic chamber. And then we also had thermocouples inside the concrete, really in the middle of the concrete at different location, emitter receiver side, and I think one in the middle, but it's not very clear. Oh, this block one, block two. Okay. And you see we vary the temperature from 20 to 30 degrees, and you see already that there is a time delay between what we impose in the chamber and what we have in the concrete. Okay, this is the story of the house filled with water. You don't have a direct temperature uniform inside the concrete block. Okay, so it means that if we want to find a law that relates temperature and wave velocity, we have to measure at the right place. If we measure in the climatic chamber, we have a time delay. So we decided to measure inside the concrete this time. So if we look at this is relative velocity variation, you see it's quite small. It's minus 0.2%, here minus 0.5%. So the reason why we can measure that is because we have very precise techniques to measure these changes. But what can we find from this graph? We find that wave velocity change is inversely proportional to temperature change. So this is the temperature, and this is the wave velocity. So when it increases, wave velocity decreases, same here. So the trend is the same for the two blocks. But this is, remember, when humidity is kept constant, of course. So, but what we also see is that although the concrete composition is identical, the trend is identical, but the magnitude of change is quite different, because here you are up to minus 0.5, here only minus 0.2. So you see that even with the same concrete, you might not have the same exact law that links temperature and wave change. So in this case, we saw that with the cork driver, we need to learn a trend or a behavior between that links the damage indicators, here, for example, the change of velocity, and environmental factor. And this will still be specific to the structure monitored. Even if you understand the physics, you saw that there is some, for example, variability in the composition of the concrete, etc., which makes it still specific to the structure. And I also showed you through the tunnel that this is useless if you are missing important environmental factors, because if you have other factors affecting than temperature and you try to fit on temperature, you get the wrong trend. You will never get rid of these things if you don't measure the right things. So the question is, since this is quite complex to do and you see all the issues, I'm not saying don't do it, but if you do it very carefully. But there is another option, which is the Swiss knife. So in the Swiss knife approach, you could probably do something without having all these problems, okay? So to explain you that, I'm going to show you an example from a colleague, Yoki Kulav. I worked on this problem a long time ago, maybe 10, 15 years ago, but so he set up in his lab a wooden bridge, and he was not measuring the temperature anywhere on the system. He was just recording and with accelerometers, and it was under ambient vibration. So basically, the ambience was making the bridge vibrate. I think it has a shaker. I'm sorry, it has a shaker here. So it was shaking constantly the system. And he was monitoring with these 15 accelerometers for a very long period of time, several months like that in the lab with changes of temperature, humidity, etc., but not measuring them. He extracted from these sets of measurement 9 mode shapes and eigenfrequencies and showed their evolution over time with these changing things. And then he did some kind of fake damage, which is that he measured for about 2,000 samples undamaged, and then he did some samples with added masses. So he put masses at different locations here to simulate a change of dynamics, let's say. So instead of reducing the stiffness, he added mass, but this is the same idea. So if you look, for example, at one of the natural frequencies here, around 23 Hertz, you see the evolution. This is all the undamaged samples, and you see that can go from, let's say, 22 to 23.5. So it's quite a change, few percent change of the frequency due to environment. And then this is what happens with the damage. So you see with the damage, you have a change here, which is much less than the change due to environment. So you would say, okay, I'm really blind to the damage here because this is taking all the variability. If I had to put threshold, it would be here, and I would never see the damage. And I will explain you how you do that later, but just to show, if you can do some statistical analysis, and you can reach what I put here. So it means that with no physical understanding of what's going on, how wood is affected by temperature, humidity, etc., just by doing a statistical analysis, you can apply that to any structure and specimen, but of course you need a training period. Okay, it means that you have to tell your statistical tool when the structure is undamaged and measure it under sufficient changing conditions to be able to get rid of that. And then you get this very nice trend here where you see that you have the undamaged sample, and clearly now the damage, the 5 added masses, you have 5 steps here of added masses, they are very clear on your diagram and you can detect that. Okay. So now I'm going to detail a bit more of theory about this. I'm sorry, there will be some equations. I hope you will not abandon me here. But I think it's important also to do some math at some point to understand a few things. So I'm going to detail methods based on the measurements of environmental factor, and then methods which are not based on this measurement. You know, the cork driver and the Swiss knife example. So types of cork drivers. If you want to fit, to have a model and understand the physics, you have different ways to do that. I mean, that's the way I would like to explain. So you have data-driven method. What does it mean? It means that your aim is to find a model and its parameters that can reproduce the relationship between the EF is environmental factors, so between the EF and the damage indicators, okay? So you need to find both the model and the parameters. In model-driven, you will derive a model from physical knowledge, so you know a bit more about the physics, what's going on, and you want to find its parameters. So usually you will do that so that the model can reproduce the relationship between the EF and damage indicators, okay? So data-driven really doesn't make any hypothesis on the type of link that exists. It doesn't know anything about the physics. It just looks at it from an experimental perspective, okay? And so the way you're going to do that is do some regression, so some fitting basically between your experiment, your environmental factors and your damage indicators, for example. And one way I put neural networks just because, you know, it's a bit specific field, but actually neural networks can also be used to do regression analysis. It's not much different from all these other methods, and I will give you a few hints about that. I don't have time to detail, but okay. In model-driven, you will actually work with analytical models that you derive from some physical knowledge, and then you need to make an inverse problem to find the parameters of this model. So in data-driven, in principle, the model is not known a priori, whereas in model-driven, you do some hypothesis and you have a model that is derived from physics. Okay, so this is an example from a paper from the state-of-the-art review that Jitendra did for the deliverable, for example. It's just showing a principle. So the principle is that you have here temperature measurements. Here you have a structural response, could be anything, a static response, a mode shape response at some point, etc. And here you see that if you plot one versus the other, you have a linear trend. And so you can do a linear regression between your measured temperature and your structural response. And based on that, you can remove the trend. So if you have this relationship, you can look at the trend here, remove it, and then you have a residual error, which should be very low if there is no change in your structure. And now if your structure changes, of course, it will react. So you have removed this trend so that, as with the wooden bridge example, at some point you can detect a change, okay? And you've done that with linear regression. Now, I want to show you that this is not so obvious to do, because if I take my two concrete block example, it looked very linearly related if you look at the data here. But actually, if you plot one versus the other, this is what you get. So for the two blocks, of course, we see that there are the different trends. One is more sensitive than the other, and the slope is more on block 2 than on block 1. But also you have some hysteresis. It's not really a straight line. And if you had been measuring only a few points, you could say, oh, yeah, this is noise on my data, and yeah, it's pretty linear. But actually, you see that it's not. There is hysteresis. And so if I do linear regression, I'll have quite some error between my prediction and my measured data. And so I will be a bit more blind to damage because I don't fit really well to the reality. Now, of course, you can do better than linear regression because you have this is really typical of a time-dependent behavior, because it's not only that it's not linear. If you go back to the same temperature, you see you have two different values, okay? So there is a time-dependent behavior. So linear regression is not accurate, but what you can do is you can do time-dependent regression, for example, with autoregressive models. I'm not a specialist of that. I've never really done it, but I read a lot about it. So for example, if you're interested, look at ARMA-X models. This is the type of autoregressive moving average with exogenous outputs. I think it means inputs or outputs. So these types of model can be fitted, but of course you have more parameter, and they take into account, in the prediction, they take into account not only the measurement at this time, but at previous times as well. So it can be used to model this theoretic behavior. Now, of course, it might be also that the relationship is not linear, and so then you can do more advanced regression analysis. So this is an example I took from the very, very nice job from Bishop. It's called Neural Networks for Pattern Recognition. And although it dates from 94, I think it's still one of the best books on neural networks applied to engineering. So if you want to do neural networks, you have to read this book, really. And you see here, okay, my data is, for example, a sine function with 10 sample points with a bit of noise. You see that if I do a linear regression, of course, I'm quite off. You see that if I use n equal 3, so a polynomial with degree 3, I'm already much better. But you see that if I use n equal 10, I'm worse. And so this is what is called overfitting. I think if you study that, you know that overfitting is a problem, but still you have to be careful about overfitting, okay? So to do all this kind of regression, you can also do that with a neural network, because a neural network is essentially in engineering used to do two things. It can be used to do regression and classification, okay? And so in the case of regression, all it does, it's going to fit a nonlinear function between input and output. So how does a neural network work? I'm here focused on the most widely used one, is the multi-layer perceptron. It has an input layer and an output layer and a hidden layer. And so input, for example, would be here my temperature measurement, okay? And my output would be my damage indicator. So I want to fit between what is the temperature and what should be my damage indicator at that point, okay? And for that, I'm using hidden layer. Why? Because basically all these input values, if you have several ones, they will combine here at each neuron. And on this neuron, you will have a so-called, I think it's activation function, okay? And this function is typically looks like that, and it's a nonlinear function. So it means that by introducing these nonlinear activation functions, I'm introducing a nonlinear relationship between my input and my output, okay? And so this threshold or activation function makes this input relationship nonlinear. But then you can show here that if you have any type of function, if you put enough of these neurons in the hidden layer, you're going to be able to approximate it with a sum of these activation functions. Here there are step functions, but they could be a bit more smooth, okay? So it means that basically what you're going to do here to set the degree of polynomial fitting, it's not polynomial fitting, but it's the number of neurons that you will use in the hidden layer that will govern how close you are to this function. But of course, we have the same problem of overfitting, is that if you put too many neurons, then it's going to start overfitting compared to your data. So, okay, that's an issue also with neural networks. So as with linear regression, etc., the network needs to be trained. So you need to feed some points so that it learns the relationship. And I'm not going into the details of that. I could spend hours doing a course on neural networks. This is not the point here. And so too many neurons is overfitting. Okay. Now, I want to also emphasize that in any regression analysis, neural networks, etc., what is really important is this idea of training, testing, and validation tests, which are not enough used in practice. So what is the idea? The idea is that, for example, in this data of the wooden bridge, I will use a training set, okay, which is this one. Okay, so I use a subset of the data to train my regression, my neural network, etc. But then I have to check that on the undamaged data, the model I've trained is also going to give undamaged data. So this is the testing set. This is really essential to have one, because if you don't have it, then, I mean, if the testing doesn't work, it means you have not trained properly. So this is ways to avoid overfitting, to choose the right models, etc. So keep in mind that this is really important because it helps to reduce the risk of overfitting and choosing the right order of the model or the right number of neurons in the hidden layer. Okay. Now, this was for the core driver. So we want to fit basically a link between environment factors and damage indicators. Now, what can we do if we don't want to do that? We don't want to measure. We want to do the wooden bridge example, the Swiss knife approach. Okay. So what is the idea? The idea is, and this is important, that if you want to do that, you have to have multiple features. So what are features? Features are basically damage indicators in this case. So you cannot do that if you have only one damage indicator. If you only have one velocity variation in medium, forget about this technique, okay? Because what you're going to do is you're going to use the correlations between these features to build a subspace to learn about what environmental factors do to these damage indicators. You will build a subspace that includes the environmental factors so that after that, you can project your data in an orthogonal, what I call an orthogonal subspace. I will show you in mathematics what it means after that, okay? Because I'm going to look basically in another direction. I look, okay, this is the direction of my changes due to environment. And now I look in the other direction to see damage. So to do that, there are two types of methods. There are the linear methods and the nonlinear methods. So I will start with the linear methods, and I want to present because they are the simplest. And okay, and also I published in 2018 a paper with Keith Worden about that, with some kind of integrated view on all these linear techniques. To me, they really boil down to the same idea. They are all the same in a sense. That's what we show in the paper. So what is the idea behind? So we have a feature vector y with dimension n. For example, we have 10 damage indicators on our structure. So we can compute the mean and we can compute the covariance matrix, which states how far this data is from the mean globally. Then we can compute something that is very difficult to pronounce, but I got used to it over the years. It's called the Mahalanobis square distance. Okay, so the Mahalanobis square distance is a distance here, as you see, which is on all the features, and it's weighted by the inverse of the covariance matrix. What does it mean? It means that when data is very far from the mean, it has not much impact on this distance. Okay. So what I did in this paper with Keith is that I worked on the spectral decomposition of the covariance matrix. So you can do an eigenvalue problem where C is your matrix and you find your eigenvectors U and your eigenvalues sigma square. Then you can show that because it's an eigenvalue problem, you have orthogonality condition. So this is going to lead to a diagonal matrix S, and your vectors here are also diagonal. And from that, you can rewrite the covariance matrix here and the inverse of the covariance matrix, okay, which is given by this here. Now, the trick here is to do a transformation by using, it's a bit like if you know mode shapes in dynamics, it's a bit the same idea, but I'm going to use as eigenvectors here the result of my spectral decomposition of my covariance matrix. And so I'm going to transform from my initial features to another subspace. I'm doing a linear transformation, so I'm not changing the size of my feature vector. I'm just rotating it in a hyperspace, let's say, of n dimensions. So if I do that, I can see that my mean here is just the product of U transpose and my initial feature vector. But what's really interesting is to see that if I do the detail of my covariance matrix, not as a function of Y, but of eta, the transform variables, it's a diagonal covariance matrix, okay? Because of this orthogonality condition. So what it means that now my Mahalanobis square distance can be written as a sum of uncorrelated distances related to all these eta values, okay? So graphically, what does it mean? It means if I have my feature vector here, which is x1 and x2, okay, that's my two damage indicators. And if I have here my set of points, you see all these points, okay? If I compute my covariance metric, do my spectral decomposition, I will find this transformation here, which brings me from x1, x2 to actually eta 1, eta 2. So this is my two, this is eta 1 and this is eta 2, okay? And yeah, I'm sorry I wrote sigma, but this is just to say that the covariance, the variance, this is to set the variance of along eta 1 and eta 2. So now I'm in a space where I have, in this axis, I have independent features, and they have a variance, which is sigma 1 and sigma 2. And you see in this case that sigma 1 is larger than sigma 2. So there is more variability in this range than in this range. So it means that when I compute this distance here, you see that all the variations that are along this line will be less taken into account because I have 1 over sigma 1 square in front of it. Whereas variations that go into this direction, they will have more weight because the 1 over sigma 2 is less, okay? So the question now is, yes, what can I do with that? So if you look at these sigma values in general, it's not rare that there is some major, in the first component, this is an example with 12 component feature vector, that the first eigenvalue, that there are a few eigenvalues, let's say, that are much larger than the other one, okay? And so you can, for example, compute the percentage to which each contributes and say, okay, I think that most of the variability here, for example, is explained by, like 90% of the variability is explained by the first 3 components, for example. So that means that I can decompose into the ones that are really explaining most of the variability and the ones that are not really explaining the variability. And actually, this is what I will call principal components, because if you do principal component analysis, if you know about this technique, also to remove environmental effect, it's exactly the same. You are doing a decomposition and looking at the most important components in the signal. This is the principal component. And then the other ones are what we call the null space. What this is the null space, it means that basically they don't explain the variability in the data as such in your data. So when this is the case, you see, this is what happens. And this is the kind of representation that you have then. It means that most of the variability in my data, as you know, is only along one direction in this example, and that there is almost no variability in this direction, okay? So if you are training, so if you are computing your covariance matrix with the data that contains all the environmental factors, then you see that this sigma 1, this direction, will be the direction in which all the environmental effects are changing your data, only along this line, and they are not changing anything along this line, okay? And so what we're going to say now is that if you use the Mahalanobis square distance, this will be very small because sigma is 1, so this will be almost 0. And so what we are going to look at here is this D2. And the hypothesis we make is that if the damage is not in the direction, and this is really important, of course, if the damage is not in the same direction as the environmental factors, then we can detect it by looking at the null space, not the principal space. Okay, so we are looking at some change of residual here orthogonal to the main direction of variation. This is an interpretation in 2D, but if you have a feature vector which is 10 or 20 or 100 dimensional, you have a hyperspace and you cannot represent it, but it's the same idea. You're going to look in the direction orthogonal to the environmental factors. Okay. Now, there is another method in linear analysis that is called factor analysis, and I will show you that this is very close to that too, but it brings another very interesting perspective to this. So in factor analysis, what you say is the following. You say that there are some factors that are affecting my data, and I don't know them, I don't measure them. But then I say that there is a nonlinear transformation that can bring from these factors to what's so-called unobservable factors. So this is other factors that result from a nonlinear transformation. And then I assume that there is a linear relationship between these unobservable factors and the features. So basically, I've done a nonlinear transformation so that I can assume that there is a linear relationship between my factors and my features. So this is the idea. And this linear mapping can be represented like this. And the idea is that if I have this linear mapping between my unobservable factors and my features, then I can always, let's say, take a measurement, find the best fit with this linear transformation, and then look at the residual. And this is what will allow me to look at damage, for example. But if you look at this, this is really equivalent to performing PCA because I'm also looking in my space of features, I'm looking for a linear relationship between my features and some things here that I can call principal components, or I can call unobservable factors, or I can call my eta values in my covariance analysis. They are all the same. They are all based on the same model. And to prove you that they are all the same, I will show you a bit in more detail, no, not in detail, but what are the results on the wooden bridge. So I already presented it to you. So in this wooden bridge, I remind you that we are completely blind to damage here. And then we have a feature vector that is of size 261. Why 261? Because if you remember, we had like 9 modes, and on each mode there is 15 accelerometers, so 9 times 15, plus also the natural frequency. So it leads to quite, and the mode shapes are complex, so it's 18 times 15, if I remember well. Well, anyway, so we are 261, so it's a very high dimensional space. And we can compute the mean, and we can compute the covariance matrix. But in the covariance matrix, we can choose to put all the data of the undamaged sample on only part of it. So I just want to illustrate the effect that it does. And from that, I'm computing this Mahalanobis distance. So remember, the Mahalanobis distance is supposed to filter out naturally the changes in the data that you trained it for, because of this 1 over sigma that comes into the distance. So this is very clear from here. If I take this data, you see that my training data here is from 0 to 300. I don't have any variability, but you see that this is not sufficient training data because the testing here still shows some variability. Probably the tests were done during maybe, I don't know, I invent January and February, and then the conditions were very different in March, April, and May, and so it's not sufficient. So then if I use 1000, you see that I can still have very flat trend on the training data, but not after, because the conditions, again, not all conditions are taken into account in my training of this Mahalanobis distance. And if I take all the undamaged sample, then this is the result I showed you before. This is working, okay? And if I compare with factor analysis and PCA, you have exactly the same graph. Okay, so this shows you that this is exactly the same techniques. I performed these two other techniques in the paper. I show it's exactly the same. So, and this is a comparison with doing nothing. This was between PCA and factor analysis, and this is compared to just putting the doing this Malan-Obi square distance approach that I explained. So there are, well, a very slight difference, but you can say that this is really identical. So it shows that there is an integrated view about all these linear techniques. And in this paper, I'm giving some insight on why and what is being done, what is the link between all these methods. Now, after dealing with these linear methods, I want to explain that there are also nonlinear methods, but I'm not going to go into detail because I'm opening a wild box of other things. But I just want to point out what are the advantages and disadvantages, ideas, etc. So in linear methods, as I showed you, you can use principal component analysis, factor analysis, or something based on the Malan-Obi square distance, and to me they all boil down to the same type of approach. In nonlinear methods, you have the nonlinear counterpart. So you have works, researcher, I've never done that, but other authors have worked on nonlinear PCA, they work on nonlinear factor analysis. Autoregressive neural networks is another way to do this kind of analysis. But what are the pros and cons? The really big advantage, of course, of linear method, it's very low computational cost. As you saw, I just have to do an eigenvalue problem, a spectral decomposition. This is very fast to do in linear algebra. And I want to stress that out, this is not restricted to a linear relationship between environmental factor and features. And why is that? I think that's why factor analysis is really interesting. It's because in factor analysis, you have this. So you see that there can be a nonlinear relationship between your environmental factors and unobservable factors. So it means that it's possible to do a linear analysis even if the link between the environmental factors and features is nonlinear. It works. And I think it's important to stress because a lot of people misunderstand that part. Okay? Now, so this is another advantage of the linear methods, but you have to understand that it generally requires high dimensional feature vector. So the more you have features, the more likely you have that some of the eigenvalues are high and some are low. And if it's not the case, if you don't have any null space, basically, it's not possible to do that. Okay? If all your singular values are the same, there is no null space. So you cannot project on something that doesn't exist. And so that's the limitation of the technique. Now, for nonlinear method, this is a very high computational cost because you have to fit nonlinear models of the data, nonlinear PCA, nonlinear factor analysis. This is really computationally expensive. But the advantage is that because the model is more flexible than the linear one, then it can work with low dimensional feature vector as well. Okay, because you don't have that restriction. You can, let's say it's easier to find a null space with less, a smaller feature vector. But the main problem is that there is a trial and error how to choose this nonlinear model because, a linear model, everybody knows what it is. A nonlinear model, there's so many different types of nonlinear models that you have to do a lot of trial and error, a lot of computations, etc. So I think it can be efficient in some cases, but I wanted to point the pros and cons of the different methods. No, I want to finish this first part with I think something that is very important and not enough addressed in many papers and many analyses on SHM is about setting thresholds. Because in the end, why are we worried about these environmental factors? It's about the setting of the thresholds, okay? It's about the fact that, for example, if you look at the wooden bridge example here, if you have environmental variability and you want to set thresholds, how are you going to do it? The only way is by saying, oh, if it goes above this line or below this line, I assume this is damage, okay? And this is not working very well. But if you then transform your data to this, for example, you see that you can probably set a threshold because this doesn't have much trend anymore. So once you have removed the trend, it's quite natural to set thresholds. But how do you do that? So the common thing about setting thresholds is that people and statisticians, or I mean, people who have done a bit of statistics, like to use the normality assumption. So they mean, okay, my variable is Gaussian, or if I have a feature vector, it's multi-Gaussian. And from this hypothesis, which I basically I've never verified, but I take as truth, I can set thresholds. So in this wooden bridge example, if you do that, assume that the feature vector, remember it was a dimension was 261, so it's a multi-Gaussian, multi-normal variable, and I'm going to set threshold, okay? So setting threshold means that on my, if I have a unidimensional Gaussian, I want to set a threshold here because I want to say that I have, for example, 99.9% confidence that this is not damage. So it means that my alpha value here is really in the tail of the distribution. I'm not like a 50% in the middle. I'm 99.9% or 99%. Okay? And if I do that with a confidence level, for example, here this is a 99.9, so 1 over 1,000 can be out of threshold, basically. Then this is what I get. Okay? So it means that my threshold is completely wrong because there's definitely much more than 1 over 1,000 points that are above threshold. There is maybe, I don't know, 10 or 15% of the points that are above threshold. So this is not a proper way to do that. What is the reason for that? It's because if you want to be in confidence level like that, you have to have a very high accuracy on your tails. And to have a very high accuracy on the tails, this is unlikely events. So even if you have a lot of samples, like 2,000, maybe only 2 or 3 will fall in the tail. And so you will not have a good representation of the tail. There is no chance, okay? And so that's always a problem, as using normality assumption for extreme statistics is nonsense. It never works, okay? So the way to do that is to use so-called extreme value statistics. And I'm not giving you the theory here, I don't have the time. But you see that if I use extreme value statistics, I'm not fitting the distribution, I'm fitting the tail of the distribution. So I'm finding a way that even though I don't have many samples, I'm able to fit quite well the tail. And it looks a bit like magic, but you see that it works, okay? So by doing that, I focus on fitting the tail, not the whole distribution. Then I have a threshold where you say, yes, I have 1 point out of 2,000 out of the confidence level. This is inside my confidence level. This is perfect for me, okay? And I've been able to set the right threshold, right? Okay, so this finishes my first part of the presentation. Maybe I can take some time for if there are just a few questions now, and otherwise we take maybe a 5 minutes break for a coffee or something. So do you have any question up to now? Yes, I'm sorry, I don't see your.
Yes. What I wanted to ask is when you train from Mahalanobis distance, right? Do you only use defect-free training data, or do you also use some data with defects in order to distinguish which direction is which?
No, you should train only data without defect because what you want to train for is the directions related to the environmental factors only.
Hmm. But could like a defect also move something in the direction of the environmental factors?
Yes,
Like,
of course. And this can happen. And this means that then you are blind to the damage. Okay?
but can you like rectify this by also training with some defect data as well, for example?
Not with the Mahalanobis distance. There
Okay.
are other techniques that you can use that are more related to classification. So when you have damaged data, then you have to use classifiers, not the Mahalanobis distance, but I didn't have time to discuss that here.
Okay, right, thanks.
Okay. Damiano, I think you had a question.
Yes. Yeah, hello, Arnaud. So if you can go back of slide, just the last topic you mentioned about the extreme value statistics.
Yes.
So this doesn't take the normality assumption and just focus on the data you have. But did you give the entirety of the 2000 samples or the same 1,800 for setting up the thresholds?
So I think here, if you look on both examples, this is the training set. So
Okay.
1,500 samples are used to set the threshold, and so
Okay.
still in the testing set you have one out of range, but it's still very good in this case.
Results, yes. Okay, yeah, I missed just the division of training and testing.
Yeah, sorry, I didn't mention it explicitly, but there was a training and a testing set in this case.
Yeah, okay, thank you.
Okay, Luigi, you have a question?
Yes, just to ask, can you go back to slide?
Great, thank you. Okay, so the second part is going to be about application, which is basically related to my research work. I hope this will help you more understand better the ideas that I presented in the first part. So, of course, for those of you who are in the network, you know that my work is on concrete monitoring and characterization, but I think we have some external guests, so I want to introduce that shortly. So when you want to monitor and characterize concrete, you can do it with destructive tests, so taking cores out of a structure and then testing it. You can also do it with non-destructive by doing resonant frequency testing or ultrasonic testing. So this is examples here with external probes. I want to introduce a bit about wave propagation in concrete and the specificity. So if you look at a sample of the microstructure of concrete, this is 5 centimeters with aggregates of 1-2 centimeters usually. And in that range, if you interrogate it at low frequency, so less than 20 kilohertz, you see that the wavelength here compared to this microstructure is quite large. But if you interrogate it higher than 100 kilohertz, then you see that the wavelength is of the order of magnitude of this sample of concrete. Okay, so it means that the waves will then interact with all these aggregates, and it will lead to some quite complex wave propagation. So if you use a pulse of here, for example, 5 or 10 microseconds at the emitter, at the receiver side, it will look like this. So if you had an homogeneous material here, the receiver side would pretty much look like this input, a 5 microsecond pulse. But here you see all these train of different waves, where you have an early or called ballistic wave, sometimes direct or ballistic, and then some later arrivals due to all the bouncing all around of the waves here in the specimen. And it can last for a long time, up to 1, 2, or 3 milliseconds in our cases. Okay. And then during lifetime of concrete, we can use these kinds of wave propagation to detect what's going on at early age and even for long term. But in my team, in my research team, we've been focusing for more than 15 years now on using embedded transducers. So the idea is to avoid having someone coming here and having to have access to the surfaces of concrete to do the monitoring by using embedded sensors. So the advantage of these transducers is that you have a very excellent coupling. So you don't need a coupling gel or something like that. You have very good repeatability because you don't move your transducers. It's rather low cost if you do a good job at making the transducers. And you can also do some internal measurements, and your sensors are protected from the outside. So this allows you to do automation of measurements with very high repeatability and no user interaction. So this is the type of embedded transducer that we have developed. We have several kinds, but the ones I'm showing here for the applications are these ones. And so they are about 25 millimeter diameter, 8 millimeter thickness. So they are not larger than a typical aggregate in concrete. So they will not disturb so much the microstructure. This is, for example, a way to fix them in a reinforced concrete beam. And we have applied them in early age monitoring, so following the setting of the concrete, also in 3-point bending tests, for example, on small or larger beams, reinforced or non-reinforced. We did a cylinder compression test also with them, and that's what I will talk about. So monitoring of the concrete repair in the tunnels, in some tunnels in Brussels. Just a word about the frequency. So by measuring the electrical impedance, we are able to see what are the resonant frequencies in different media of our transducers. So you see that they are all in the range of, let's say, around 150, 120 to 180 kilohertz. So this is the range of resonance of our transducer, but you see that the frequencies are different if you are in the concrete than if you are outside. Okay, now I want to say a little word about time stretching. Why I want to do that? Because for me, this is the foundation of the cork driver approach that we do to this. So some physical understanding of what's going on. So I had a PhD student who did this very nice, I think, presentation. Maybe I showed it to some of you in the past, I don't remember. But so to explain what is time stretching, he said, okay, assume that you have a few guys who need to do a hike, and so they need to go through the mountains and reach the campsite here, okay? But of course, they will all take different directions independently. Some things, oh, I will go faster if I go between the mountains, or some will go on top, etc. So they will arrive in a different order because they follow different paths, okay? And there will be one winner, the first one. So if you have a lot of these guys, then probably there's some really good ones. They will arrive before the others, and then there will be a whole crowd which will arrive about at the same time, and then some late ones who maybe they got tired or injured during the week. And so if you look at that, this is a bit what happens with your wave, is that first you have like the champion is coming, the first wave here, and then you have a whole bunch of people, there's more energy here, a whole bunch of people, and then some late ones arriving. So this is what your wave will look like. But then what happens, for example, if the weather changes? So one day it's sunny and then it's more clouded, and here it's more cold. So maybe you can assume that when it's very sunny, people will be slowed down because, you know, it's hard to walk when you're in full sun. Maybe you don't have enough water, etc. So it means that probably the crowd will arrive later if there is a lot of sun than if it's cold, because cold weather is better condition to do hiking usually, okay? But so looking at that, if the effect of all these temperatures is the same on all these guys, they will all slow down or speed up by the same amount. So it means that in the end, major hypothesis that you do is that if you look at this one, if you stretch it, you will arrive to this one or this one, okay? You just pull on the image and you will see that the spacing here is always proportional. So it means that the main hypothesis that we make when we use time stretching is that if the velocity change due to environmental factor is uniform in the medium, then time stretching can be used to compensate fully for them. Okay, but for that, you have to have really that the velocity change is the same everywhere, so that in all the path travel, the change of time is also always proportional to the total time. And then you can use time stretching to compensate. Okay, so stretching in time is our core driver that we would like to use, but remember, this is the hypothesis is that we have this uniform velocity change. So how do we find this velocity? How do we do this time stretching in practice? We use the correlation coefficient, which I already introduced before, which is basically 1 if the waves are the same. So we assume that if we take, and I'm sorry, maybe the stretching should not be on the reference signal, but on the other one, but it doesn't change much. So we assume that if we stretch one wave compared to the other one, then there is an optimum where CC is maximum, and then we find what is the stretching factor. And hopefully, when we have done the stretching factor is the CC, the correlation coefficient is 1, which means then that our major hypothesis is met. Okay? So of course, in this analysis, you see there is T0 and TF, and so we can choose really if we stretch the whole signal on only part of it. So for example, we introduced something where we do stretching only on the first part and not on the full signal. So that requires a reference signals and test repeatability, and so that's good because we can do that with embedded transducers. So if you perform that, you will see that at your optimum, your CC is high or close to 1 if the general shape of your wave has not changed. Okay? Then it will give you information about this uniform velocity change in the medium. But the CC will decrease when you have local modifications in the media, because if you have one obstacle in the middle of the media, it will change the way the wave packages arrive, so it will change the shape, okay? It's a non-uniform velocity chain. In this case, you will see its impact. Okay, so I just want to show you a first application, which is not directly an environmental effect, it's more operational conditions, but just to show you that's the first thing we did in the lab. So here we are, what our aim was to monitor a 3-point bending test on a concrete specimen that you see here with two embedded transducers. So what happens is that we wanted to do the monitoring during the test. So we don't remove after a certain load, do the test and come back. So we do it while we are applying the load, okay? And so what happens when you apply a load to concrete is that due to the stress on the concrete specimen, you're going to have a change of wave velocity due to this stress, okay? And so you're going to have two confounding effects. One is the effect of the load, and one is the effect of the cracking that starts to occur. And so we want to detect damage and not the change of load. So our major hypothesis is that velocity change due to applied load is pretty much uniform, that's the major hypothesis, in the region where the wave has traveled. And this is called acoustoelastic effect, the fact that the wave velocity changes with load. Now, you can already see that this major hypothesis is not completely true, because if you know a bit about structural engineering, you know that when you do a 3-point bending test, you don't induce uniform stress in your specimen. You have maximum stress in the middle and 0 stress on the sides. So what you are interrogating here is between the two transducers, but also what is to the left and to the right, because there is some wave going backwards, bouncing everywhere, coming back, etc. So you see already it's not completely true. Okay, so what we found actually is that indeed, if we do coda wave interferometry on the whole signal, it doesn't work well to get rid of the acoustoelastic effect. And one of the reasons is that the stress is not uniform. So if we focus on the first wave arrival here, then we are really interrogating something that is around the transducers where the stress is not changing too much. But we also assume that when you put a load like this, you can have slipping here on the supports, okay? So if you record waves that travel up to there, you could see the influence of that, of the boundary conditions that changed during the test. So that's why we decided to focus more on the early wave than the full wave to do our analysis of time stretching. And actually, you can see here that with this time stretching, we're able to record some velocity change in the medium. So points 1, 2, and 3 here on the force displacement curve, you see that up to point 1 and a bit later, you're in the linear phase, which means there is no damage in my specimen. And then when I reach point 2, I have quite some damage. And then I start unloading after point 2. And so this is what happens here. So you see that indeed the Coda wave interferometry, if you take the full time signal, you're not able to catch well the velocity variation that occurs. If we look at the first wave arrival, you see that you're able to catch this change, so decrease of wave velocity. And then when you unload, you have partial closure of the cracks, and so the wave velocity re-increases a little bit. If you are using time of flight, so just using some methods like Akaike information criteria to catch the wave velocity, this is what you get, but you see that you have a lot of scattering. Here we did some fitting because we had a lot of data, but if you look at the individual points, the precision is about 1%, 2%, so it's not enough to really follow well the evolution. But if you zoom on the first part here, what do you see? The first part here is up to this point. So we are here still in the linear range, okay? And in the linear range, you see that if you look at our technique, the direct wave interferometry, we called it, you see that you see really change of velocity already here when there is no damage. Of course, there is a jump here. Not sure exactly why that is, but we also see this change. And so this we identify as the acoustoelastic effect because we have no damage, but the wave velocity starts changing in this range here. So that's our acoustoelastic effect. So now we also computed, so we did this time stretching and we computed what we call a decorrelation coefficient. So it's 1 minus the correlation coefficient, just to invert the axis. So it's 0 when there is no change and it will increase when there is change. And you see that if you do it with Coda wave interferometry, it starts really reacting very early here. But if you do it with the direct wave interferometry, what do you see? You see that it's pretty flat, but there is some reaction here of the damage indicator before the real damage occurs. And so again, this is the acoustoelastic effect. So in this case, at that time, we were working on the damage indicator, which is basically looking at the difference, the integral of the difference of the waves just on the first wave arrival, so on this one here, okay? But what we did is we used time stretching on these first wave signals to compensate for the acoustoelastic effect. So when we compensate with time stretching, you see that our signals align much better, but we still are able to catch a difference in amplitude here in our damage indicator. So bottom line is, if we do the time stretching on the early wave, you see that we get the blue curve. Whereas if we don't do the time stretching, we have the green curve, which you see reacts here around 0.1 before there is damage, and even a bit before. So we see that time stretching is efficient to remove the acoustoelastic effect, providing you do it on the early wave, etc. You pay some attention to these things. But then the question is, now that we remove the trend, how do we set the threshold? Okay, because this is important. How do we detect that there is damage? So we did some work in a conference paper in 2019 where we also used this extreme value statistic and normal assumption threshold here. And you see that we are able to set a threshold which reacts to damage, but if we don't remove the trend due to acoustoelastic effect, you see that it will react here before damage actually occurs. So it shows the efficiency of using this time stretching to get rid of the acoustoelastic effect. Now I want to focus on an application in the tunnels and explain you how we transpose all these ideas to tunnels, because tunnels, unfortunately, is more complex than this acoustoelastic effect that I just told you about. So the idea, what happened in Brussels, so in 2016, I think a block of concrete fell on a car. Unfortunately, there was no one injured, but it really sets a lot of things in movement to make repairs in all the tunnels. This is the Brussels region. You see, we have all these underground tunnels here going almost around the city, and also some tunnels here in this area. So we have the problem of aging of this infrastructure. inspection is not generalized, was not generalized, only visual inspection. So in Brussels, they decided to do visual inspections, chemical and mechanical tests on samples, but this all needed to require to close the tunnels. And if you, for those of you who live in Brussels, think about Jitendra and Damiano, you know that if you drive a car, it's a nightmare when you close tunnels. It's really problematic, and so we want to avoid that in the future. But that was used to decide on repair actions, and I think that in the future, what we would like is to have automated system that can detect early damage to avoid these extensive campaigns of testing, closing tunnels, unmounting all the panels in front, etc., etc. So what we want is to make the infrastructure more available, and of course avoid having blocks of concrete falling on people's car. So we did a first instrumentation in 2019, so already 5 years ago now, in the Rogier tunnel. So this tunnel is about 800-meter tunnel, I think, in the north of Brussels. And we put these transducers. So what was our idea? So we wanted to use a so-called core driver approach to start. So the repairs were done like this. They destroyed the bad quality concrete. They did some passive evasion of reinforcement bar, and they put some new concrete on top, and for the cracks, some injection. So the idea was how to assess this quality of repair. Was it done properly, and how it evolves with time. So what we propose is this is one zone where concrete, you see, concrete was visually inspected, and maybe also they knocked on the concrete, etc. They decided this is a bad part, so they hydro demolish, so it's high pressure water to remove the concrete there. And then they are going to put some repair here. So what we decided is to put embedded transducers inside the old concrete. So why inside the old concrete? Because if we try to put them in the new, there's a big risk that workers are going to damage the transducers when repairing. So we wanted to be safe with that. So we put them inside the old concrete and then let them repair. And the idea was that if there is a cavity, if this new concrete here or mortar is not attaching correctly to the concrete, it will create cavities or detachment. And so we can see that in the ultrasonic signals. That was the idea. Of course, we wanted to also compensate for environmental effects. And for that, we have to have the fact that the velocity change due to this environmental factor is uniform in the region where the wave has traveled. I have shown you from the beginning that this is the main hypothesis that we make. This is our physical understanding. This is our core driver. So in the tunnel, we had different repaired zones, so 1, 2, 3, and 4, where concrete was removed and then repaired. So we put pairs of transducer all there, but we also wanted to have a reference pair, so we put a reference pair in an unrepaired zone. We have now a better system, but we had this system here with a computer, and the data was recorded, etc. Installation of transducers, because it's old concrete, we drill a hole because it's quite small transducer. We put the transducer, we seal it, and then we have our transducers sending waves. So we have this system where at the time we were measuring every 30 minutes, and we were sending different types of signals, so the pulse at different amplitudes and the burst at different amplitudes and frequencies. And we have remote access to reconfigure, to get access to the data. And then we did some processing on our server. We're looking at the data every day with some reporting, okay? So what were we using as damage indexes? Well, what can we use as damage indexes? So if we use this time stretching, you know that the outcome of the analysis is an epsilon, a time stretching, which if the correlation coefficient is high enough, can be interpreted as a relative change of velocity. And then we decided to use the decorrelation coefficient, so 1 minus this, as a damage indicator. So we have two things to look at. So this is a first result of, we installed the system in June 2019, and this is pretty much, okay, if we look here until this point where the system was down for a few days, we have about 1 month of recording. And so you see that during this month, we had, of course, temperature variation, daily temperature variations, and some trend downwards here. It was a bit more hot in the beginning, at the end of June, than in the middle of July. And if you look further here, you see there's some higher temperatures, okay? But this is representing our decorrelation coefficient. So you see that the wave is quite decorrelated. You see this is increasing. And you can see in the DC that, well, there was some repair here at that point. So you see it reacts to the repair. But it also reacts to environmental factor, because you really see these waves here. They are related to the change of daily temperature. And maybe this wave here is related to this kind of trend like this. Okay, so it's reacting to both. Even though we have used time stretching, okay? So that means that our major core driver hypothesis is not valid. We cannot compensate just by time stretching in real conditions in a tunnel. It doesn't work well enough. So at the time, Cedric, who was my PhD student, no, he was a postdoc at the time, he proposed something else. He said, well, obviously, yes, the hypothesis that this wave velocity change is uniform is not right. But maybe what we can do is to use a shifted reference, an average reference. So he said, let's use the average of the stretch signal during the last 48 hours as a reference. So instead of taking a reference here in the beginning, let's shift it and average it over 2 days, okay? And by doing that, he went from this graph to this graph. So you see that in this graph, we clearly pick repair works in 2 zones, 39 and 40. And then here, repair works in 2 other zones. And the other zones, they don't react at that time. And we get rid of all these variations here due to temperature, the general trend, etc. Okay? So we thought, okay, that's a nice way to do. Let's do that. Even though we don't fully understand why it works, it seems to work. So on top of that, if you look at velocity variations, which is the second plot, we also have something very nice when we do this averaging. You see that clearly on 2 zones, we have an increase of wave velocity after repair. And then after about a month, it tends to be constant or not changing that much anymore. This is normal. This is a property of concrete. It hardens in the beginning and then stays constant. Usually it's mature after about a month. And clearly, again, we see these 2 zones repaired here and 2 zones repaired here. And then for the non-repaired zone, we see that there is not this increase, but we do have a jump here that we don't understand. So it could be linked to the way we post-process, or something happened maybe on that day, because you never know what happens. There are works every night in the tunnels. Did someone attach something in the zone, do something? We don't know. We don't have all the information. But you see that we've also been able to get the velocity variations due to setting and efficiently filter the ones from an environment, because you don't see much trend here, a little bit more. Okay, now that was to monitor the settings of the beginning, and so that allows us to make sure that the repair is okay, that we have an increase of wave velocity, everything is going well in the repair. But then we want to monitor for a longer term. So what do we do for the longer term? If you look now, still with the same post-processing technique at the change of velocity over time, this is about, I think, 1 year. So from January 1st to about, end of November 2020. So you see that, of course, we have a temperature range that's quite much larger than before. We can go from 10 degrees to 30 degrees with some daily variation, with some loss of data as well. That's the reality of monitoring. But then we see these velocity variations, and you clearly see that they are linked to the temperature variation. So when the temperature increases, the velocity tends to decrease. This is kind of stuff that we saw in the concrete block. So the trend is similar. And if you look at the DC, the decorrelation coefficient, you see that, yeah, it still reacts to temperature, because even though it's not as high when you have a repair, you have at some times here DC up to 0.4. This is quite high, 0.2, 0.3. So we are, even with this technique, we are not able to have really something flat. And you see that putting thresholds on this is complicated, because there's still some trend related to maybe the high temperatures, etc., in the data. So what did we do? We said, okay, we use our core driver to the best of our knowledge. We did time stretching. We even proposed to do an averaging of the signals to get things better. And it worked quite well for the early age, the setting, but for the long term, it's not perfect. So we decided, why not to add the Swiss knife to that, to add something. And so what was the idea behind the Swiss knife approach for this tunnel? Well, up to now, all we have done is to work on zones independently. But all these zones, you see, they are in the same region, so they are subject to the same environmental conditions. So we have 4 zones, not 5, because the signal was lost in one of the zones during the part of the monitoring, so we didn't look at it. And we were using 3 excitation signals, so 1 pulse and 2 bursts at 40 and 80 kilohertz. So it means that basically we have a vector of 12 features, 12 damage indicators, 4 times 3. So that means we could use this Swiss knife approach, because all these features are affected by the same trends, environmental trends. So indeed, if you compute the covariance matrix for these 12 features over a year, and you look at the sigma values, so the spectral decomposition that I showed before, you see that indeed most of the variability in the first 1, 2, or 3 values here, okay? So that's interesting, that maybe we can filter using this Mahalanobis squared distance approach. And that's what we do. So we take the 12 feature vector and we apply the Mahalanobis squared distance. And remember, this Mahalanobis squared distance, it filters out naturally the environmental effects, okay? And so I think, I'm sorry, training sample, the training samples are, so in this case, we took training samples, which are a subset of all, but spread throughout the year to have really the variability all over the year. So we have the training samples, and then all samples at the red points are not used for training. So they are used as a testing set, as I explained before. And you see that it works really well. I have 1 or 2 points here above. I can even set thresholds, 99, 99.9, and I can really have something that is below threshold and that would react, hopefully, if some damage occurs, okay? But the problem with that is that it's a global indicator. So it tells me that something is going on in maybe one of the zones. But I designed the system to be able to detect what is happening in each specific zone. So now I would like to have information on each specific zone and not a global indicator, but go back to my local indicators in each zone. So to do that, I'm going to introduce a little more theory than before. We did some filter back transformation, because you see this transformation from my feature vector. If I have my transformed orthogonal space that I detailed before, I can do the back transformation, because this is a square metric, so I can go one or the other way. But when I do the back transformation, I have to be careful that I don't introduce in the back transformation too much of the environmental factors. So what we did is that instead of using the eta, we use a eta prime, which is weighted by the inverse of the sigma values. So if the variability is large on my eta values, then my eta prime is almost 0. That means I take out of my back transformation, I filter out the environmental effects, just with this rule here that we said, Okay, so it means that the first three, for example, they will have almost no contribution because their sigma value is high and it's a sigma squared. So it's even worse. And if I do that, this is what I get. You see that compared to what I had before when I had DCs going up to 0.4, well, okay, I have two outliers here, but for the rest, everything now in all the zones is flat. And if it's flat, it means I can set thresholds on these individual values. And so this is what I had before. And now with my Swiss knife, this is what I get. You see, it's much better with the filtered back transformation. And it's so good that I can set the threshold. So this is a threshold on one of the zones, zone 39 now. I can look at my indicator, put my threshold also with extreme value statistics, if I remember well. And you see that except for maybe 1 point, when you have 1 point out of line in a chart like that, it's really not a problem. You can filter it out as an outlier. It's just one event. But you see that now we can set the threshold at 99.9% and really monitor and see what's going to happen. Okay. So the only thing that we miss in this application is, and this is what we discussed already in some of the questions for the first part, is, okay, but are we still able to detect damage? Okay. Unfortunately, I cannot give you the answer for the tunnels because Brussels mobility will not allow me to re-damage regions which were repaired. Okay, so I have no way, unless there is a damage that appears in the coming years, I have no way to check that this is still sensitive to damage, that I'm not filtering too much by doing all I have done here. Okay, so what are my conclusions of this part? So I showed you that in the tunnel example, my core drive, I first tried to apply a core driver, which is a time stretching. That this time stretching was based on the hypothesis that the wave velocity change is uniform in the medium, and obviously it's not. That's why we introduced some averaging moving reference, which improved the situation, but was still not completely perfect. So that's why we use, I call principal component analysis, because this backfile filter transformation is basically a principal component or minor component analysis. So I introduced some Swiss knife here to take into account correlations. And you see that this Swiss knife doesn't depend on the physical model or anything. It's just a straightforward linear method to filter out and learn. And by doing that, I was able to efficiently filter this environmental factor to set some thresholds, but there are open questions. So like I said, this moving average, we used 48 hours. It was more like a, let's try and see what it gives. But part of Jitendra's work is to look at, okay, is it 48 hours or should it be based, for example, on, I think it should be based on the change of temperature, of daily temperature, which can be different in winter and summer. So maybe we can adapt and tune that a little bit better. And maybe there are also alternative methods than this time stretching. So Jitendra already looked at phase corrections, MWCS methods, all kind of things. So this is really the PhD of Jitendra, about what else can we do to do that. Should we use more of a core driver approach with more physical understanding, or other Swiss knife approaches to that? And then the last point, of course, that I just mentioned before is that you have to be sure, or you should make sure that damage can still be detected after filtering your environmental factors. I told you that I'm not allowed to do that in tunnels, but we are allowed to do that on small specimen, and we have a climatic chamber. So this is also the goal in Jitendra's thesis, is to study first undamaged specimen, define these new alternative methods to do the filtering, but then put a specimen in mechanical loading machines to induce damage, and then to check if those methods that Jitendra will develop with me in the thesis will still be able to detect the damage. Of course, this is very important that this is the case. Okay, so this finishes my second part with the application, and well, I'm just open to questions that you may have about all this. But thank you. Yes, Luigi.